So, in this module, we are continuing the discussion of what is lexical scoping, and in the previous module we had discussed about some basic concepts of lexical scoping, some of the examples which takes values from the global environment and something like that. We have fixed some functions which tells us how actually lexical scoping works. But in this example, we will let you know some different kinds of things which are associated with lexical scoping. We will let you know what inflict operator actually is. We will show you how the functions like missing with these functions, what the syntax of these kinds of functions are and how these functions work. We will show you some examples associated with these many functions. We will also tell you what the global environment and what other kinds of environment actually is, and how values can be defined within these kinds of examples. Although you may know some of the details regarding these kinds of environments, but still we will give you some recapitulatory lesson regarding this. So, let us see what we can learn from this module. So, here we are starting with the idea that every operation is a function call. To understand computations in R, two slogans are helpful, like everything that exists is an object and everything that happens is a function call. These two are by John Chambers. This includes infix operators like plus, control flow operators like for, if and while, subsetting operators like the one which is given as third bracket and dollar, and even the curly brace. Now, here this should be noted that the backtick lets you refer to functions or variables that have otherwise reserved or illegal names. You might have find these kinds of errors which are associated with backtick, like if you put backtick within your code, then otherwise you may find that an error message there. Now, let us consider a simple example. Here x is assigned to be 10, y is assigned to be 5, and hence x plus y is equal to 15. This is very simple example, and everybody can do this. Now, let us do this with the help of what we have learned so far. If we write this R code, then we are having exactly the same thing which x plus y gives us, and it gives us 15. So, we are using infix operator plus here. Let us consider another example. This is quite different, but it's indeed very simple. Here, suppose x is taking the values of a vector 1 to 10, and if we use this code here, then what R will give us? It will give us the sixth value of the variable of the vector that we have defined, of the x vector that we have defined, and it is defined to be, and it is given to be 6. Again, if we use for here within that backtick and for loop, and if I takes the value 1 and 2, and if we are required to have required to print the values of I, then what do we have? We are having 1 and 2 as the output that is given. Now, let us again use a curly brace, and here we need to have 1 and 2. We need to print 1 and 2, better to say. So, what we are having is 1 and 2 as a output. Here it should be noted that the backtick lets you refer to functions. Here in R, as we know that R is a functional programming language, we have learned many things regarding this. R provides many tools for the creation and manipulation of functions. You can do anything with functions. You have already learned these things about these of the features of R, and you know how the functions can be treated in R. You can assign them to variables, store them in lists, pass them as arguments to other functions, create them inside functions, and even return them as the result of a function. So, you can do it all the things which can be done with vectors, matrices, list and other higher dimensional. So, here let us assign the numbers 1 to 10 are vectors of numbers vectors which contains the numbers 1 to 10 within X. So, now we are using for here, and then within the for loop basically we are using a conditional statement if. Now, here we are trying to have if I divided by 2 is not equal to 0. So, if they are odd numbers, then we need to print the odd values, that is the exact values which we are giving, the values of I, and otherwise we need to print dash. We have come across these kinds of functions before, but we haven't used these operators before. So, this is something which we are having as an output. We are having all the odd values, odd numbers starting from 1 to 10, and again in place of the even numbers we are having dash. As we have directed, exactly the same thing we are having here, but we are having here with the help of the new operator that we have learned. So, it is also possible to override the definitions of these special functions, but this is almost certainly a bad idea. However, there are occasions when it might be useful. It allows you to do something that would have otherwise been impossible. For example, this feature makes it possible for the dplyr package to translate R expressions into SQL expressions. Domain specific languages uses this idea to create the thing that allows you to concisely express new concepts using existing R constructors. It's more often useful to treat special functions as ordinary functions. For example, we could use supply function to add 3 to every element of a list by first defining a function add, like the one we have given here. Here we have defined a function prod, which is defined to be a function of x and y, and it is basically x into y. And if we use this prod function in the place of the function that are given as argument within the supply function, then what do we have? We are inputting data as 1 to supply, and in place of the place in the place where we need to put the data, there we are putting 1 to 5. Then in place of the function we are having prod and then 2. So, basically we are having 2, 4, 6, 8 and 10 as our output, as it is expected from it. But we can also get the same effect by using the built-in function which is called product. Look at this, here we are having supply, then 1 to 5, then we are using that built-in function product and then 2. So, we are having exactly the same thing which we had in the previous case. For the next R code, here as well we are writing supply, then 1 to 5, then we are having this subtraction operator and then 2. So, this will give you the output which is given here. So, basically what we are having is that we are using this built-in function instead of the function that we have specified, but we can use both the things as we have seen here. Now, suppose you had a list of function arguments. Now, how could you then send that list to a mean function? Here you need to use do.call. A more useful application is to combine lapply or supply function with subsetting. Let us see how it works, how it does all the things. Here let us have a list which contains 1 to 3, then 4 to 8 and then 9 to 12, and we are assigning all these numbers within the variable x. Now if we write down this code, then what R is doing is giving us is that it is giving us 3, 6 and 11. Basically the supply function is giving us with these many arguments and these operators. This is basically giving us the third values corresponding to each of the elements of the list. So for 1 to 3 the third element is 3, for 4 to 8 the third element is 6, and for 9 to 12 the third element is 11, and that is what we are having here. Now suppose our y is a list of 1 to 10. You can observe that this is a list, you know that this is a list because this is given within the list function. So how could you calculate the mean of this list? You need do.call function, and then what you need to insert as an argument, you need to give do.call, then within first bracket mean comma y. And let us see what we are having here. Basically we are having here the mean of the 10 numbers 1 to 10, and which is 5.5. The default value can be defined in terms of other arguments. Let us have a look at the g function. Here the function is basically which specifies a is equal to 2 and b is equal to a square, and here we are having the vector of c of ab. So the output should be given like that, and if we ask for the g function here, then we are having this thing that 2 and 4. Again if we give g10, then this will give this will return us 10 and then twice of 10, that is 20. Default arguments can even be defined in terms of variables created within the function. Just have a look at this. This is a function. This g function contains the values a is equal to 2 and b is equal to d, and within the body of the function we are defining d is equal to 4 into a, and the output is and we are having this CAB within this body. So if you want to have the g function now, then we are having 2 and 8 in this form, and if you want to have g of 5, then what do we have? We will have 5 and then 4 into 5, that is 20. So this is what the output says. Just see how the missing function works. Here we are having a function I, which is a function of a and b, and here we need to have the output like c of missing a, missing b. That is what we want to get. So if we want to know just this I and then within the first bracket, so we are not putting any argument here, then as it is expected both the arguments are missing, both the a's and b's are missing. So we are having both the outputs as true comma true, since missing a is equal to true and missing b is equal to true. Instead, as you can expect, if you write down I of a is equal to 1, so a is there but b is missing, so a is missing is false, so we are having false in the first place, and b is missing is true because there is no b, so we are having true here. Exactly the same thing is happening for I b is equal to 2 as well. Here also, since a is equal to missing, so this a is equal to missing statement is true, so we are having true in the first place, and in the second place we are having b is there, so b is equal to missing is false, so exactly we are having b is equal to missing. Sometimes a non-trivial default value may take several lines of code to compute. In that situation, missing function is very helpful. So we have other aspects of using missing functions as well. However, it is sometimes hard to know which arguments are required and which are optional. In that situation, set the default value to null and use is.null function to check if the argument was supplied. You might have come across these kinds of arguments before this as well. Let's see what the with function actually does. The with function applies an expression to a data set. As we can know, the general syntax is with, then within first bracket data comma expression, where data is usually a list or data frame, although other options also exist, but primarily these two are used mostly. And the expression, we can have one or more expressions to evaluate using data, where the commands must be wrapped in braces. So, let us see how it works. Here, suppose time is equal to 2 to 7 and demand is equal to these 6 elements which are given within a vector, and we are adding 1 with the demand vector. So, first we need to make a data frame. Here our t is 2 to 7 and we are having these many values within the demand vector, and then we are having a data frame with time is equal to t and demand is equal to the variable within which we have put all the values of six many demands, that is d, m and d. So, our data frame contains 2 of the elements, time and demand. Now, we will use with function here. So, we are writing down these many arguments within our with function, and look at the output that we are having. We have these as our argument, as you can see. So, R always tries to bind a value to a symbol. To do that, R searches through a series of environments to find the appropriate value. When you need to retrieve the value of an R object, you should at first search the global environment first for a symbol name matching with the one requested, and then search the namespaces of each of the packages on the search list. You can use search function for search list. The first element of the search function list is always the global environment. The last element of the search list is always the base package. The order of the search list always matters. When someone loads a package with the library, the namespace of that package goes to the position 2 of the search list and everything else gets shifted down the list. R has separate namespaces for functions and non-functions. Let us have a very simple example here to demonstrate this. Here a is taken to be 10, then we are having a function f which contains print a. So, if you ask for the function f, it simply gives you 10. It is very obvious now. So, in this example, what is the global environment? The environment where it finds the value for a as 10 is global environment. In the previous example, what is the current environment? Inside the function where the function value of a as 10 is not defined. Now, consider another example. Here a is equal to 10. We are again defining a function f where a is equal to 5. Within this, again we are defining a function g which has been encapsulated within the function f, and in g we are wanting to have print a. So, basically we are wanting to print a, and then what we are getting is if we want to have f here, we are basically having the printed values of a, that is 5. In the previous example, value of a is not defined in the current environment inside the g function. So, R looks for the value of a defined in the parent environment. The parent environment here is the place inside the function where a is equal to 5 is defined. So, when R finds the value for a search process stops here. If value of a is not found in the parent environment, what happens then? Then R continues search further to parent of parent environment, which is obviously global environment in this case, and the value of a would have become 10. Consider another example. Here f is a function, and here within the f function we are having g, which is a plus b, and here what we are having is we are specifying a is equal to 10, and then when we want to have h, then we are again defining h is equal to a function which contains within that a is equal to 100, b is equal to 200, and then f we are taking the instance of the function f here, which was made with g as well. So, this is what the function looks like. Now, suppose b is equal to 5. Now, without running this program, predict what value h should return. Here h will return 15, but why we are getting this? Because R looks for the value of a and b which are defined in the global environment. R did not pick up the values 100 or 200 what we are giving here. Instead, R picked up a is equal to 10 in the call g, and the global environment b is equal to 5. So, let us quickly have another function which is called cube. We all know this is the cube of a function, and here this is shown to be a function of n, and so first we are defining a square function, and then we will define a cube function with the help of this. So, let us see what will happen here. Here we are defining a cube function which is a function of n, then we are having this within this function, and then we are multiplying n with this square function. So, basically again we are encapsulating a function within another. So, this is a real life example which we can construct always, and if we write down cube 3, then this will return 27. So, variable n in the function square is not an argument. So, it is a free variable, and under lexical scoping it is the parameter to the function cube. It is the active binding for the variable n when the function sq or square was defined. Now, here consider another example. Here we are again defining f to be a function of x and y to be y is equal to 2x, and we are wanting to know print x, print y and print z. So, here x is a formal parameter, y is a local parameter, and z is a free parameter as you free variable, as you may know. The body of a function can be divided into 3 classes: formal parameters, local variables and free variables. The formal parameters belong to the argument list of the function. Values of such parameters are determined by the process of binding the actual function arguments to the formal parameters. Local variables are determined by the evaluation of expressions in the body of the functions. Variables which are not either formal parameters or local variables are called the remaining one, that is the free variables, and if free variables are assigned, then they become local variables, as you may know. So, as you can see from this module, we have learnt about several new ideas which are associated with the lexical scoping. Here we came to know about what infix operator actually does and how to use backtick without any error. And here we have also come to know about the use of functions like missing, with, and several other functions. We also learned how we can use Laplace and supply functions along with the subsetting operators. So many things that are there which were discussed here, and still there are many things which can be discussed regarding this lexical scoping in R, but we are stopping here, and from the next module onwards we will start discussing about considering a new topic. So we are stopping here.